hold on. Okay. I think I'm recording. I didn't hear my notification, so I'm just a tiny bit concerned here. But I think it's recording. And okay, so let's talk about the final. You know what? Let me open up a Word document because I can type faster than I can write, and I'll put all of these notes online. Okay, so this will be our description of the final exam. Okay, so it will be mostly multiple choice. Well, it'll just be sorry, multiple choice and short answer, like short numeric answer. I think that's kind of been the case here, right? Exam is 110 minutes long, 4 p.m. to 5:50 p.m. Okay, it is synchronous, so everyone take the exam at the same time. Everyone log into Zoom, Proctoring. Cameras on, mics muted. Okay, and this is to ensure students are taking the exam alone. So I don't think you guys would do this, but I have heard stories of, because of all of these online courses, I have heard stories of kind of students getting together and basically doing like a group exam. When it's all done remotely. So, I hope nobody did that for the quizzes, but at least for the final exam, it's kind of a high stakes thing. So we're going to enforce a little bit of proctoring here. Okay, I won't be recording. Cameras on, mics muted. I will not record video or anything like that. Okay, so. Okay, I'm still working out the exact length of the exam. Okay. Oh, wait, a few more things. Okay, so open notes, open book, calculator. Actually, you'll probably need to calculator. You can use that. No talking with other students. Or communicating students, posting questions to forums or Chegg or other sites. Okay. I think that's obvious, but sometimes people will catch people doing stuff. Okay. Exact length to be determined. Okay, exact length. How many questions? I'm still kind of working this out, but I'll tell you at least some of the questions. Okay, there will be a section of theoretic questions. Let's say theoretic or conceptual questions. Okay. So questions, a section, so maybe somewhere from 5 to 10. Again, 5 to 10 theoretic. We'll just write that. Theoretic or conceptual questions covering, like hypotheses, p-values, meanings of 1 or type 2, confidence levels, everything kind of related there, interpretations, all of these conceptual questions. Yeah, so when is the final? Well, the final is going to be in place of our Thursday lecture. Okay, exams 120 on Thursday. What is that? July 29th, right? July 29th is Thursday. Yeah, okay. Yes, thank you. Okay, yes, and then I will not record video, and after you submit the exam, so just make sure everybody's okay. And then we had a question for the final where you'd use calculators to find standard deviation. Yeah, of course, yes. All right. Okay, so there's going to be a section on conceptual questions. Then I will have maybe approximately 5 questions covering which statistical method test for a given scenario. Okay, and then the rest will be a bunch of so again, this part I'm not quite sure how many questions. So somewhere between 20 to 25 questions on different statistical methods, right? And so we covered for mu1 quantity, mu1 minus mu2, t-test for 2 independent samples. We have the approximate Mann-Whitney non. I'm spelling this correctly. T-test for samples. So I don't think I can fit everything. So some of these topics will be covered on the exam and some will not be covered on the exam. So, my apologies in advance, if you spend time like memorizing some of this stuff. I mean, you don't have to memorize anything. Everything's open book, but you spend time studying it and then you're like, man, he didn't even put it on the exam. And, that's just how, just how things go sometimes, right? So I don't think I'll be able to fit everything. There's just kind of too much here to put in like a 2-hour time span. We have a question. Are we allowed to use tablets and iPads? Yeah. Will there be the option of submitting our scratch work for partial credit like the quizzes? I'm putting this up for debate. I'm leaning towards weighting all of the questions a little bit less, like, or kind of weighting them equally, and then you just kind of get the points or you don't. But I'll consider this. Yeah, I'll think about this scratch work business. So that's also TBD. It's just the scratch work delays the grading, and I want to try to get your final grades filed away, but I'll think about it. Okay. So anyway, 20 to 25 questions on, these are the different statistical methods that we've covered. And then, and so questions that could be asked. Be something, you know, could be asked will be like, present some data and a description, or some, you know, description of the scenario. And then you'll have related questions. So such as, you know, hypotheses for the test, error, you know, statistic, conclusion. So, okay. Oh, and then I'm sorry, there was one more thing in here. Confidence interval. Oh, we had it. For okay. Or if we're talking about a confidence interval, you know, it's the upper bound, lower bound. Right? Okay. Is that okay? Are there any questions about this stuff? Let's see. Will we have quiz 5 graded before the final, or the key to quiz 5 before the final to help study? I don't know. I don't know. Let's see. I don't know if I can get quiz 5 graded right away, but you know what? Okay. Well, I'll ask the grader how quickly they can get this thing turned around. But I don't want to make any promises if I can't keep them, but we'll try. Okay. Any questions here regarding stuff? So this part I think is kind of like what you've seen in the quizzes, right? So I think a lot of the quizzes in the past have been, at least quiz 3, 4, and 5, I think, were kind of in this format where, you know, I would present a little bit of data and then have some questions related to it. Okay. And so this is going to kind of be in this section of, you know, 20 to 25 questions or so. So there. Okay. What is the penalty for late quizzes? You know, I don't know. I'm sorry, you're catching me. I don't remember off the top of my head what our what we do. Let me get back to you on that. Okay. Yeah, so the exam is designed to take kind of the full 110 minutes. I'm not sure how much time you will have left over. Of course, this is going to depend from student to student. Some students work much faster than others. The goal is to kind of target something that's maybe around 2.5 times to 3 times the length of one of the weekly quizzes. Okay. So something around, yeah, 2.5 to 3 times the length of a weekly quiz is kind of the target length for the exam. And again, you can expect a handful of theoretical questions or conceptual questions, a handful of kind of questions covering which statistical method or test we should use for a given scenario. Okay, and then I'm going to have a whole bunch of questions. Probably I will select a handful of these and then do so what are there? There's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. I'll probably pick like 8 of these topics, something in here, and then do maybe like 3 questions or so related to each of those 8-ish topics. Okay, like, 8 plus or minus and 3 plus or minus a couple of questions. Okay, so it'll be like, here's some data, and I want you to do a Wilcoxon-Whitney non-parametric test. And if that were the case, what would be the hypotheses and what would be the related p-value and what's the conclusion that you'd make or something. Okay. Or, here's some data, and, please perform a chi-squared goodness of fit test. And what are the, what's the test statistic and something like that, right? Any further questions here? So go ahead. Yes, and so this one just okay. So stats 13. Doc X. Okay. So I will post this. Okay, and I have a few questions that we can kind of go over for, say, like theoretical conceptual question examples, but these are not going to be, so the problem with doing like some sample conceptual questions is, of course, I'm not going to ask these exact same questions on the final exam. So, some people might complain that these questions were nothing like the ones on the final, but of course I'm not going to give you the same questions here that I'm going to give on the final. But that's we'll do a few kind of practice ones, and yeah, I think it's okay. All right, so let me put them out here, and let me just kind of copy and paste them here. Okay. Oh, here we go. I think I can get this to work. All right. So off screen here. All right. So here's a sample question. The significance level alpha is used to decide whether or not to reject the nil hypothesis. What else is alpha equal to? And these are your answer choices. Let's, what are your reactions? What reactions do we have? Because we don't have A, B, C, D. We have clap, hand, joy, and open mouth, surprise. Okay, so I guess clap. Crying, laughing, and surprise. I don't know, is this dumb? Do we not want to go over the answers? Okay. What's your answer? You guys are able to see my screen? Do I need to make this bigger? Okay, all right. Well, Okay, so not all right, all right. We got 10 people answering and they put clap hands, and that is correct. Okay, so that is the answer. So probability of mistakenly rejecting the null hypothesis when the null hypothesis is true. This is the type 1 error. Okay. Clap. Great. Okay, I'll give you another question that I've written on here. Again, let me replace this with clap. Thumbs up. I only have a handful of these questions here. And again, they won't be exactly the same on the final. Oh, I was not planning on doing a view quiz for today's lecture. Thank you for coming though. I appreciate you guys being here, but I was not going to do a view quiz if that's okay. All right, so I have this question. Imagine a criminal court case with the following hypotheses: defendant is innocent versus defendant is guilty. Based on the way the American justice system has been created, would we want a large alpha or small alpha? And these are your answer choices. And let's hold off on giving our answers. I guess I'll count to. I'll give you guys a few seconds to think about this, and then we'll share our answers all at the same time. Okay. All right, go ahead and let's see your answers here. So we've got 21 surprises, a couple of clapping hands and thumbs up and things. Okay, all right. Yes, the answer here is the surprise face. So silly that we're doing our multiple choice quizzes this way, but type 1 error is convicting an innocent person. This is worse. We want to avoid this by using small alpha. Ideally, we can get more evidence that will either strengthen or weaken our, the case. But there's a way you can do a poll on Zoom. I know you can do a poll on Zoom, but that requires, I think you have to like create it. Oh, I guess it's not so hard. But then I don't even know if it's going to be recorded in the video. So this is okay. This is very informal and I don't actually care. Like we're not using this for any kind of credit. It's just to give you a little bit of interactivity. But yes, that is a good idea to use the actual technology that's available here. Okay, here's another, I guess, a lot of these, I guess, are type 1, type 2 error related. Why isn't type 2 error worse? Okay, so type 2 error is bad. There's no denying that. Type 2 error is bad. Type 2 would be letting a guilty person go free. And there's always room for debate here as far as, is it better to let a guilty person go free or is it better to convict an innocent person? And I mean, better is not the right word. Is it worse? Is it worse to let a guilty person go or is it worse to convict an innocent person? And Again, room to disagree. I think overall, again, just with the way our justice system has been created, it's supposed to say that convicting an innocent person is worse. I think there were kind of a few papers, but I don't remember my history very well. But someone said, I'd rather let 10 guilty people go than to convict an innocent person. And I think that's kind of how it's set up. But yeah, of course, we don't want to let guilty people off the hook. Certainly families who, perhaps, the victims want justice and they deserve justice. And of course, seeing somebody guilty go is also a failure of justice. It's, I don't know. I don't think we're going to be able to settle this debate in a small discussion here. Okay. There was a question. It says, another question. What if we thought that we didn't want a guilty person to be found innocent and go free? Sorry, I was just confused. Okay, yeah. Okay, same question. Yeah. So again, I will try to avoid. Again, both of these, type 1 and type 2 error is worse. We're going to go with type 1 error is worse here. Okay. I'll try to pick one. As far as the final exam goes, I'll try to make it, if I were to put a question like that, I'll try to make it unambiguous about which one would be worse. Okay. Okay. What would a type 2 error be in this scenario? The null hypothesis. So doctor diagnosing a patient. The test used the following hypotheses. The patient has no cancer versus the patient does have cancer. And what would a type 2 error be in this scenario? So again, I'll give you guys a few. Some of you have already put your answer choices there, but I was going to give you just a couple of seconds to think about this. But I guess go ahead, if you know your answer, go ahead and put that up. And yes, the answer here would be clapping. In terms of, this is 2 error, negative, null hypothesis false and should be rejected. And so that means does have cancer. Okay. That the diagnosis. So that would be type 2 error. Okay. All right, so here is, we'll do one more here. And here, this time, don't give us your answer until we'll do it as a group. Okay, so it says a researcher conducts a hypothesis test with a non-directional alternative, so a type 2 two-sided test, and calculates the p-value. If the researcher had decided to do a hypothesis test with the same data, but with a directional alternative, a one-sided test, how would the resulting p-value compare, all right? And so your choices are the p-value of the one-sided test would be smaller, or I'm sorry, if the researcher decided to do a hypothesis test with the same data, but with a directional alternative, how would have the resulting p-value compared? The p-value of the one-sided test would have been smaller than the p-value of the two-sided test. The p-value of the one-sided test would have been larger than the p-value of the two-sided test, or it would depend on the direction of the hypotheses. The resulting p-value could be smaller or larger, or the entire test would need to be done again to find the p-value. All right, so think about this one. And all right, let's I'll count to 3 here, and we'll reveal our answers. Okay, ready? 1, 2, and 3. Go ahead and reveal your answers. Okay, all right, so we got a lot of people clapping. We have some laugh, cry, and we have some thumbs up here. Okay, and so the answer is laugh, cry. It's that it would depend on the direction of the alternative hypothesis. The resulting p-value could be smaller or larger. So I know this might sound as a surprise for a lot of you because a lot of you selected clap. And so if the data align with the direction of the p-value, then the one-sided test have a p-value, I'm sorry, direction, not of the p-value, direction of the alternative hypothesis. And the one-sided test will have a p-value half of the p-value of the two-sided test. So, you know, like for the t-test, you multiply the p-value by, or the tail area by 2 if it's non-directional, and if it's, you know, for something like the chi-squared test or something like that, you know, if it's two-sided, you just leave it as is, and if it's one-sided, you just you divide by 2 or something like that. Okay, but so I wrote hint, don't forget about checking directionality. Okay, however, if the data do not align with the direction of the alternative, then you will have no evidence to support the alternative, which means you have a very large p-value. And in fact, the p-value will be over 0.5. So for example, alternative says, you know, medication lowers blood pressure. The data goes with those who took the medication have higher blood pressure, right? So higher blood pressure than those who took placebo. In this case, okay. Will you be giving hints on the actual exam questions too? Probably not. I mean, maybe. I guess I'll. It's usually not my intention to like trap students and be like, ha ha ha. I got you. But if I do write like a question and I think, oh, you know what, this might be hard, maybe I'll provide a small hint. But in general, probably not. Probably not. Okay. But we have that. Okay. Is this so these are the types of questions you might see, like not, of course, not any of these exact questions, but you might see questions kind of like this in the as far as this part, 5 to 10 theoretic conceptual questions. And so these are going to cover things like hypotheses, p-values, the meanings of alpha, beta, type 1 or type 2 error, confidence levels and interpretations, things like that, that cover a lot of these statistical inference types things. Okay, let's go over which statistical method or test we should use in a given scenario, okay? Are there any questions before I go on? Okay, then let me go ahead and draw a bit of a map here. So I'll post this and then I'll draw a bunch of stuff here. Okay, so all right, which statistical test or method should we use? Okay. All right, and this is going to be a simplified version of figure 13.1.1 in the textbook. So there's a similar diagram like this in the textbook, but it's more complicated. Okay, so first we take a look at our data, and we will ask, do we have a numeric response variable? Or do we have a categorical response variable? Okay. All right, so let's go ahead and take a look at the numeric response variable. And so we might have a situation where we have no predictor or no associated variable. All right, and so in that case, we would just do a confidence interval. And I'm going to just abbreviate these CI from here on for mu, confidence interval for the mean of the population mu. Okay, and then we can also have a numeric predictor variable. So we have no predictor. We might have a predictor variable, and if we have a numeric predictor variable, okay, let's see, numeric predictor variable, what statistical test or statistical method? All right, we can draw scatter plots. We can calculate correlation. We can do linear regression. All right, and this is all covered in chapter 12. All right, and then we have a whole bunch of stuff here. If we have a categorical predictor variable, okay, so categorical predictor variable, let's let's do only 2 groups. Okay, and then we'll have 2 or more categories. All right, so if we have 2 or more categories and they're all independent groups, we can do one-way ANOVA. And that's in chapter 11. Okay. But then as far as having 2 groups, we have independent groups, and we will have paired data. Okay, if we have pair independent groups, we can assume the sampling distribution is normal. And if so, then we would do a t-test for independent groups. That's chapter 7. Or we can do a confidence interval where the quantity mu1 minus mu2. That'd be chapter 6. So assuming sampling distribution is normal, I guess CL2 central limit theorem is applied. Okay. On the other hand, if we do no CLT, no central limit theorem, so that would be a small sample and data has outliers. And we've got independent groups. What do you guys think? What test do we use here? So independent groups, no central limit theorem, small sample of data, the data has outliers. All right, no takers. All right, we're gonna do the Wilcoxon-Mann-Whitney. So I'm gonna just abbreviate this. Wilcoxon-Mann-Whitney, non-parametric. And that's chapter 7. I think section 10. Okay. Is that okay? So will we have to distinguish between similar tests like signed test and signed rank test? Yeah, so those get kind of applied to the same scenario. So I won't be mean and I won't tell you like, oh, why did you use the signed test here and not the signed rank test or something? So so I think at least the questions on the final, I'll make sure have a unambiguous answer, or at least yeah, I'm trying to be fair, okay? That's my goal, is to try to be fair, okay? So for paired data, okay, so if you're, I guess we'll just do parametric. That will be the paired t-test. And then you can also have non-parametric. So paired t-test is chapter 8. And all of these are chapter 8. Non-parametric, you have the sign test, which is weak. And you have the signed rank test. And this is technically the Wilcoxon signed rank test. And so both of these are all chapter 8. Okay, so that's what we have there. All right, categorical response variable. we can have no predictor. Okay, so then in this case, we can have confidence interval for P if there's only if only two categories, or just really one category, but either it's in it or not. And then you can also have the chi-squared goodness of fit test. And this is from chapter 9, and this is for 2+ categories, so 2 or more categories. Okay, question, can you explain the main difference between parametric? All right, so I'm sorry. Oh, I missed a couple questions here. Will you be putting headers for the types of questions on the final like you do on the quizzes? Yeah. So there will be like I guess like a title to the question, right? So I'll put little question titles that I guess give a little bit of a header, but I don't want to say they might not be as telling as perhaps the quiz, the headers that appear on the quizzes. Okay, let's see. What exactly is a predictor variable? So the predictor variable, so sometimes, when you have data or a scenario, you'll have, the variable that we're recording is usually a response. And then there's usually maybe like a secondary variable. And, as far as this, we can treat it as the explanatory variable, the predictor variable, the input variable, something where we're looking for some kind of relationship between the variable that we've recorded and this other variable, right? So we might say like, is the blood pressure different between these two groups? Is the weight gained different for the different diets for the lambs and things like that? So in those cases, blood pressure and weight gained would be the response variable, but then like the different groups, the different diets, those would be your predictor variables. And so, so sometimes those predictor variables can be categorical. Sometimes those predictor variables can be numeric. So, so that's what we have. Okay, can I explain the main difference between parametric and non-parametric again? So the parametric means you are willing to say the sampling distribution follows this distributional shape. I'm trying to look for a simpler way to say it, but basically, I mean, as far as this class goes, and the difference between parametric and non-parametric is a little bit more general than this. But as far as this class goes, if you're willing to apply the central limit theorem, if you're willing to say that the thing follows a normal distribution, that's going to be parametric. And if you're in a situation where perhaps you have a small sample, perhaps your data has these outliers where you say, you know what, I don't know if I should apply the central limit theorem, then we use a non-parametric test. So non-parametric test, the values themselves don't actually matter. It's just kind of how big, like you're comparing values. Like, is this value bigger than this value? That's how non-parametric values work. So like in parametric, you're looking at the actual number, like 50 versus 3, and you go, oh, there's a difference of 47. That's big. But in non-parametric, you're just saying like, is this one bigger than this one? So like when you do the Wilcoxon-Mann-Whitney, you're just looking at each number here, and you're just saying, is it bigger than the other numbers in the other column? And you just say, how many numbers is it bigger than? Okay. When you do the sign test, you say, is it bigger or smaller? Did I get a positive or negative change? Wilcoxon sign rank test, again, you're just kind of ranking them from least to greatest. The actual numbers don't matter, but just the rankings from, which one's the biggest and which one's the smallest. You do that. And that's kind of a common thing that happens to non-parametric. But in general, I mean, as far as this class goes, we're only going to worry about the central limit theorem. And if you can apply the central limit theorem, it's going to be parametric. And if you're unwilling to do that, we'll use a non-parametric one. Okay. All right. So if you have no predictor, you can use the confidence interval for P. You can use a chi-squared goodness of fit test. You can have a categorical predictor. And this will be the chi-squared test for independence. So this one is our, do Californians and Texans drive pickup trucks at different, are there different proportions of Californians and Texans that drive pickup trucks, right? That's the chi-squared test for independence. Are those variables independent? Okay, not covered is this one. If you have a categorical response and a numeric predictor. So I will just say this. This is not covered in our class, but you might wonder, right? So if you got no predictor, numeric predictor, categorical predictor for numeric response, it also makes sense that you'd have these things, right? Categorical response, no predictor, categorical predictor, numeric predictor, not covered in class. This would be something called logistic regression. Or other classification models. Okay, there's a question. It says, do you think you can write down the example for the predictor again? I'm sorry, I'm still a little bit confused. What? So a predictor variable is just, I guess, any kind of variable we are using to help us either improve or tell if there's a difference, right? So when you do like a hypothesis test, a t-test for the mean of population 1 and the mean of population 2, what distinguishes population 1 from population 2? There's a variable that says, oh, these individuals belong in population 1 and these individuals belong in population 2. That variable, it would be kind of the categorical predictor. So for example, if you're doing, is there a difference in heights between men and women or something like that? You know, in that case, gender would be the predictor variable, and the height is the thing that we're looking at, would be the response variable. So we're looking at the height. This is the variable we're recording, and we're asking, is there a difference between the mean of one group and the mean of the other group? And in this example, the groups are based on gender, and so gender would be the predictor variable. Okay, if you're looking at, is there a difference in the number of, I think one of the answers, number of blocks that the young adults could complete versus the seniors, okay? So in that case, the categorical predictor would be age, young adults versus seniors. That's the grouping variable. And then the response variable is numeric, and that's the number of blocks that they were able to complete. All right, is this, is that okay? I hope that's okay. All right, so I have a few problems that we can take a look at here. Let me see if I can get this to. So let's try a few examples. Okay. All right, so we're looking at chapter 13, Let's look at this first problem here, okay? Researchers conducted a randomized, double-blind clinical trial in which some patients with schizophrenia, oh, you know what, I'm sorry. Let me, before we get, I jumped ahead of myself, okay? There's one more thing I want to kind of cover, which is, before we get into some example problems, I want to go over all of the different hypotheses for all of the different tests that we've covered, okay? Okay, so we have the t-test for independent samples. Okay, and that sample 1 and sample 2 are unrelated. Okay, so here the null hypothesis is always mu1 is equal to mu2. Okay, this can also be written as that the difference between mu1 minus mu2 is 0, that there's no difference there, okay? In words, we can write something like population 1 and population 2 have equal means. So again, we're always talking about the population and the means of the populations, okay? And then your alternatives could be, you know, mu1 is not equal to mu2, or mu1 is greater than mu2, or mu1 is less than mu2, or, you know, also mu1 minus mu2 doesn't equal 0, or mu1 minus mu2 is greater than 0, or mu1 minus is less than 0. Okay, so that's what we have for the t-test for independent samples. Okay, and then we have the Wilcoxon-Mann-Whitney test. Okay, and this is non-parametric. And what that means is there's no symbols in the hypotheses. No symbols in the hypotheses and no reference to the mean. Okay, so I think a few of you got that question wrong on one of the quizzes, where it, you know, it said, what are the hypotheses? And what the hypotheses were all in words, but one of them said like the mean difference is this, or the mean is of one group is this and something. And the Wilcoxon-Mann-Whitney, we don't talk about the mean, okay? It's, so the null hypothesis would be something like both populations have the same distribution. Okay, and then a non-directional alternative would be something like one of the populations tends to, has a distribution that is shifted higher. We can write that. or another way to write it is that tends to produce larger values than the other population. Okay, or you could have a directional alternative. All right, and the directional alternative would be that population 1, has a distribution that is shifted higher than population 2, or population 1 tends to produce larger values than population 2. Okay. All right, we have the t-test for paired data. Okay, and so in this case, we only look at the difference. Okay, and so the null hypothesis here is that the mean difference is equal to 0, or we would write the population mean difference is 0. Or that there is no population mean difference. That's another way of saying it's equal to 0. Okay, and then the alternative, you could write that the mean difference is not 0, or the mean difference is greater than 0, or the mean difference is less than 0. Right. The sign test for paired data. Okay. The null hypothesis, again, these are non-parametric, so no symbols, right? The null hypothesis would be something along the lines of the differences are just as likely to be positive as they are to be negative. Okay, and then the alternative is so non-directional. Would be differences are more likely to have one sign over the other, not specifying which one. So here you're just kind of taking a difference between, your before and your after, or, observation 1 versus observation 2, whatever it is, because when you have paired data, you're taking multiple observations from or multiple measurements from the same observation or same individual. Okay, and then your directional, depending on it, would be something like the differences, before minus after are more likely to be positive, and you specify the sign. More likely to be positive. Okay, so that's some of them. And I'll save this and I'll post all of this up, and then but we still have more tests that we've covered, right? Are your notes slides included? Open note, open book? Yes, of course. Of course, you can use my notes and my slides and the stuff I've posted on the website as you take the exam. That's what it means to be open note and open book, is you can use this material here. Okay, is this okay? Can I go to the next slide? Anybody still just kind of curiously copying things down, need me to slow down? I'm gonna go, I'm gonna flip it. Okay, and then you have the Wilcoxon sign rank test. Okay, and this one, the hypothesis is especially kind of tricky here. And that kind of, the null hypothesis would be positive differences and negative differences are tends to be equal in magnitude. Okay, so here we're just, again, we're not talking about the mean. So all of these non-parametric things, the hypotheses are always so weird, is that they're never about the mean. Okay, they're just kind of about the values, how big the values are. So here we're talking about like the magnitude, and here we're talking about positive differences versus negative differences. Okay, and then a non-directional alternative will be that will something be like positive differences and negative differences are unequal in magnitude. And a directional alternative, and I'll just, you can flip the direction just by switching the words positive and negative, and you can say positive differences tends to have a greater magnitude than negative differences, greater or lesser, right? That would be something along the lines of the hypotheses we would use for the Wilcoxon sign rank test. The non-parametric hypotheses are always the most uncomfortable ones to write. All right, let's keep going here. So I'm just kind of going in chapter order. Chapter 7, chapter 8, now we're in chapter 9. And so we have the chi-squared goodness of fit test. And here, the null hypothesis is basically is a list of proportions or probabilities. So I'm making this up for some example, right? So the null hypothesis will say the probability of category A is equal to 0.4. The probability of category B is 0.35. And the probability of category C is 0.25. 25. And the alternative will be at least one of these listed proportions is wrong. Okay. All right, so moving on to chapter 10, we have the chi-squared test for independence. Your null hypothesis would be probability of A given B is equal to the probability of A given not B. So whether A or B, and B has happened or not, it has no influence on the probability of A happening. The null hypothesis in words can be expressed as A and B are independent. Okay, and then your alternatives could be probability of A given B is not equal to the probability of A given not B, or that would be non-directional, right? And this one would be directional. Probability of A given B is greater than the probability of A given not B. Okay, and of course, you can change greater than or less than, whatever it needs. Okay, chapter 11, we covered one-way ANOVA. And our null hypothesis would be that the mean of group 1 is equal to the mean of group 2, equal to the mean of group 3. The alternative would be at least one mu is different, or however many groups you have. Of course, you list them all. And that's it for one-way ANOVA. I'll just keep it simple. Again, if you enjoyed this class and you're interested in more statistics, you might consider another class in ANOVA or something like that. More complicated ANOVA. All right, and then in chapter 12, we learned the test for significance of correlation. And here, our null hypothesis is that the correlation in the population is 0. So there's, we would write something like, there's no correlation between X and Y in the population. And then the alternative would be something like the correlation is not 0, or, you know, the correlation is greater than 0, or the correlation is less than 0, or something along those lines. Okay. I think that's all of the different hypothesis tests that we've covered in our class. Which tests are non-parametric besides Wilcoxon-Mann-Whitney? So Wilcoxon-Mann-Whitney is non-parametric, the sign test is non-parametric, and the signed rank test is non-parametric. So those are the non-parametric tests that we've covered in our class. So anything Wilcoxon is non-parametric. So you have Wilcoxon-Mann-Whitney, Wilcoxon, sign rank, and then yeah, the sign test. So if it has sign or Wilcoxon in it, it's non-parametric. Yeah, everything else is parametric. Okay. Questions? We're good? Okay, so for the remaining portion of our lecture, or I guess our review session, I was planning on just doing some example problems. If you have any questions, so I want this to be useful for you guys. Hopefully, putting these things on the screen was helpful. Sometimes just being able to kind of put everything in one section, like which test to use in one section, and listing all the hypotheses just on kind of one section is helpful. Even though all of that information, I think we've seen before, but it's just kind of like spread out across like 10 different notes, PDFs, each of like 100 pages. So hopefully putting it in one section was helpful. If you don't have specific questions, I was going to work through a handful of questions here. And so the first one is this one right here. And this says, researchers conducted a randomized double-blind clinical trial in which some patients with schizophrenia were given the drug clozapine and others were given haloperidol. After 1 year, 61 of 163 patients in the clozapine group showed clinically important improvement in symptoms, compared with 51 out of 159 in the haloperidol group. Identify the type of statistical method that is appropriate for the data. And then it says, but don't actually conduct the analysis. We'll actually go ahead and conduct the analysis. So I want you guys to think about this problem here. And what do you guys think? If you can enter in the chat what you think the appropriate test to use would be, right? So think about, what is our response variable? And what is our kind of predictor variable? Just what are we going to use to separate the groups? You can think of this as predictor or grouping variable. All right, so what do you guys think as far as which test we should use? Okay, well, nobody wanted to answer. Well, what is our response variable? And what kind of variable is it? What's our response variable? So they are looking to see if the patients showed clinically important improvement in symptoms. All right, so our response variable is improvement in symptoms. Okay, and this is going to be kind of a yes or no. Did they improve? Yes or no? And so this is a categorical variable. So we have a categorical response. Okay, and what's our predictor variable? Our predictor is, our grouping variable is, we've got the clozapine group versus the haloperidol group, okay? So this is going to be drug type. And this is also categorical. Okay, so we have two categorical variables. We're looking to see if there's a relationship between two categorical variables. So what is the appropriate test to use in this case? Okay. Oh, okay. I was gonna say you guys are gonna break my test here, or break my heart here, but let's see. So we've got a few suggestions here. So our answer is the chi-squared test for independence. Okay, because we've got a categorical variable and a categorical variable. And so, and one of those in the slide from a couple minutes ago, I don't know where I put it. I got to find it, but categorical variable response, categorical predictor. We're going to look at the chi-squared test for independence. Okay. What would our null hypothesis be? So we're going to say improvement in symptoms is independent of drug type. So this is basically saying that who got which drug is not going to, it didn't matter whether they got one drug or the other drug, who improve, the proportion of people who improve is just the same for both groups, okay? So we're gonna say probability of improvement in symptoms, okay? And so that requires an expert, right? You know, a psychiatrist needs to evaluate whether the patient has shown improvement in symptoms, okay? Improvement in symptoms, if given clozapine, is the same as the improvement in symptoms given haloperidol. Okay, that would be our null hypothesis, right? And then the alternative would be that they are not independent, that drug type does make a difference. And here, it doesn't say that they're looking to see if clozapine is better or worse than haloperidol or anything like that. So we're just going to leave it non-directional. And I'm just going to write I for improvement given clozapine not equal to the proportion of improvement given the other drug H. All right. Is this okay? I hope. All right. So then what we would need to do is we need to organize our observed data for the chi-square test for independence. We're going to organize our observed data into, we'll make a two-way table here. Got a 2x2 table. We have, I've got clozapine, haloperidol. We've got 163 patients in clozapine, and we'll write improved, did not improve, 61, 102, 159 here. So I have 51 out of 159 improved, which means 108 did not improve. Then I'll add across the rows. And our total 61 plus 51 will be 112. 102 plus 108 is 210. No, yes. And then this is going to be 322 for the total. Okay. So then we'll do expected. So if the null hypothesis were true, what are the numbers we would expect? All right. So we'll copy the totals. Okay, so our expected count if the null hypothesis were true, it's going to be the row total times the column total divided by grand total. So one of the things about the final exam is not that the problems themselves are suddenly hard. It's just you got all of these problems, and it's not going to be like, this is from chapter 11 or this is from chapter 10. So you're going to be doing chi-squared. I might have a question where I'll say like, do a chi-squared test for independence or something like that, but you still have to kind of, figure out like, okay, how am I supposed to do this, right? So, it is open note, and you can use my notes, but I would recommend kind of, because I think all of my PDFs, there's probably like several hundred pages there, right? I would say make a few sheets on regular pieces of paper that kind of, list off what to do for each test, right? You say like, okay, if we got the chi-squared test for independence, this is what I need to do, right? If we've got the chi-squared goodness of fit test, this is what I need to do. These are the steps. And I would just say like, kind of just make a, boil it down to just one page for each kind of test. And then, then you can have like a, 6 pages front and back or something. And I think that's going to be more manageable than having to flip through several hundred pages of notes there. Okay, so I think if you do this so I did the work a little bit earlier. I got 56.7, so I'm going to go ahead and plug that in here. So if I plug in 56.7, the other numbers total out. So we'll get 106.3, 103.7. Right, and then our chi-squared test statistic is we're going to do observed minus expected, quantity squared over expected. We're going to do, so we'll go through each cell, all 4 inner cells, 61 minus 56.7 squared, over 56.7, plus the next one, 51 minus 55.3 squared over 55.3, plus the next one, which is 102 minus 106.3 squared over 106.3. And the last one, 108 minus 103.7 squared over 103.7. Okay. And then I think if you you get this, you will get 1.013. This is your chi-squared test statistic, and we will look this up with degrees of freedom equal to 1. For a two-way table, you got 1 degree of freedom. And then from there, you can get your p-value and get your answer. All right, so hopefully this feels familiar and comfortable. I hope. Okay. Let's, all right, thanks for that thumbs up there. All right, let's look at the next one here. Okay, so it says a biologist collected data on the height in inches and peak expiratory flow, a measure of how much air a person can expire, measured in liters per minute for 10 different women. Here are the data. Subject 1, height 63, peak expiratory flow 410, so on and so forth. We have this recorded for 10 different people. And the question is peak expiratory flow related to height? Identify the type of statistical method that is appropriate for this data, but don't actually conduct the analysis. Let's go ahead and actually conduct the analysis. But yeah, go ahead and look at this. And what do you guys think? What is the appropriate method and test that we should complete here? So anyone else with suggestions for answers? Okay. All right. Yeah. So let's so what we want to know is if there's a relationship between height and peak expiratory flow. And so we actually have two variables. We have height and peak expiratory flow, and we have two measurements for each person, but we're seeing if there's a relationship between those things. And so we are going to do correlation. So the appropriate test. So we have a numeric variable and a numeric variable, two numeric variables. So we are going to do correlation, right? All right, and I see someone suggested a paired t-test. And, if we were looking at the same measurement that was measured twice, right? So if we had like a height of subject one, and then we measured height of subject one after we did something, correlation would, not correlation, a paired t-test would make sense. Or if we did like, so if you were like, the height of a plant before and the height of the plant after, then a paired t-test would make sense. So a paired t-test, so I understand why somebody might have suggested paired t-test, because we're getting two measurements from the same subject, right? But as for a paired t-test, for it to be a paired t-test, it's got to be kind of like the same variable measured multiple times. Okay, so it's like same variable measured multiple times. So I think we had examples where I don't know, like weight before and weight after or something, something like that. And here we've got two different variables. They're both numeric, so we're going to do correlation here. Okay, maybe let's go ahead and calculate the correlation by hand, just for let's just do these 5. Okay, so the full data set, there's 10 people, but let's just go ahead and do correlation for let's calculate the correlation for these 5 observations. Okay, so I'll call height X, peak expiratory flow Y, and so if I plug in, if I calculate the mean of X for these 5 observations, so I've done this work already, I'm going to get 64.2. The standard deviation of X is 1.304. The mean of Y is 430. And the standard deviation of Y is 62.048. Okay. And so what I'm going to do is I'm going to go ahead and make a few columns here. I'm going to have X minus X bar, Y minus Y bar. The product X minus X bar times Y minus Y bar. Okay, so 63 minus 64.2, I get negative 1.2. 63 minus 64.2, I get negative 1.2 again. 66 minus 64.2, I get 1.8. 65 minus 64.2, I get 0.8. 64 minus 64.2, I get negative 0.2. Y minus Y bar, 410 minus 430, negative 20. 440 minus 430, positive 10. 450 minus 430, 20. 510 minus 430, 80. And 340 minus 430, negative 90. Okay. And so I'll take the product of these two things, and we'll get 24. We'll get negative 12. We'll get positive 36. We'll get positive 64. And here we'll get positive 18. So the sum is going to equal 130. Right? So the formula for correlation, 1 over n minus 1 1 over standard deviation of x, 1 over the standard deviation of y, times the sum of x minus x bar, y minus y bar. All right, 1 over 4, 1 over 1.304, 1 over 62.048 times 130. I get a correlation of 0.4017. Okay, and so we'll ask, is the correlation significant? Okay, so in this case, our null hypothesis, rho equals 0, or alternative, we'll say rho is not equal to 0. Okay, our test statistic is a t statistic, and it is r times the square root of n minus 2 divided by 1 minus r squared. Right, so I'm going to put 0.4017 times the square root of 5 minus 2 divided by 1 minus 0.4017 squared. And I get t is equal to 0.7598, okay? And we will look this up with degrees of freedom equal to n minus 2 with 3 degrees of freedom, okay? And basically, if you do that, you'll get your p-value, right? And then you'll multiply it by 2 tail times 2, right? So you get a p-value greater than 40%, and that's going to mean do not reject the null hypothesis. Okay. Is that okay? So far, so good. All right. What if we take a look at this question? It says, consider the data of exercise 1323. Maria is 1 inch taller than Annika. Using the information from exercise 1223 or 1323, how much greater would you predict Maria's PEF to be than Annika's? Okay, so this is basically asking, what is the slope of the regression line? Yeah, so the question is, can we conclude that the correlation is not significant? Yeah, so if these were if we only had 5 data points, the correlation is not significant, not significantly different from 0. Okay, so slope of the regression line. Slope of the regression line is r times the standard deviation of y divided by the standard deviation of x. So we're going to have 0.4017 times 62.048 divided by 1.304. And get 19.11. Okay, so we'll say if Maria is 1 inch taller than Annika, we predict her peak expiratory flow to be 19.11, what is that, liters per minute, greater than Annika's. Okay. Okay. We might run out of time to do too many more exercises here. Let's let's take a look at a couple more examples here. So 13.2.5 says a geneticist self-pollinated pink flowered snapdragon plants and produced 97 progeny with the following colors: 22 red plants, 52 pink plants, and 23 white plants. The purpose of this experiment was to investigate a genetic model that states that the probabilities of red, pink, and white are 0.25, 0.5, and 0.25. Identify the type of statistical method, and that is appropriate. Okay, so what do you guys think? Yeah, this would be a chi-squared goodness of fit test, exactly. Okay, and in this case, our null hypothesis would be the probability of red is 0.25, probability of pink is 0.5, and the probability of white is 0.25, okay? The alternative, at least one is wrong. Okay, and then let me just, so we have observed, we have expected. I want to actually go through all of this. So we got red, pink, white, okay? We observed 22, 52, 23. Our total is 97, okay? And so the expected is going to be 97 times 0.25, 24.25. It would be 97 times 0.5. We would have 48.5. 97 times 0.25. Okay, and then we won't bother, but you'll sum this up. Observed minus expected squared over expected. Okay, we'll get some number. Figure that out. Okay, let's keep going here. Okay, actually we haven't learned that one. Okay, 13.2.8. Says biologists were interested in the distribution of trees in a wooded area. They intend to use the number of trees per 100 square meter plot as their unit of measurements. However, they were concerned that the shapes of the plots might affect the data collection. To investigate the possibility, they counted the number of trees in square plots, round plots, and rectangular plots, and the data are shown in the following table. What type of analysis is appropriate for this data? So we've got the count of how many trees that showed up in a square plot, the count that showed up in a round plot, the count that showed up in a rectangular plot, and we want to know, what should we do here? Okay, question. It says, I'm a little late in the asking, but from 13.2.3, why did we double the p-value for alternative is non-directional? I think 13.2.3 was it's a t-test. We do a t-test, right? So, and the t-table for non-directional, you double it. So the t-table only gives you one tail, one direction, and for non-directional, you double it. So whenever you're doing the t-test, if it's non-directional, you double it, and if it's directional, you kind of leave it. But for all the other ones, chi-squared, and the other ones, your Wilcoxon and Whitney and things like that, the tables always give you the non-directional, and if it's directional, you divide by 2. Yeah, it's a little bit, it's a little confusing, but that's how these things are given. Okay, so what do you guys think? 13.2.8, what kind of tests do we have here? So we have a numeric outcome, and we have categorical response with three categories. So we will do one-way ANOVA. Exactly. Right. So our null hypothesis here would be that mean of the square is equal to mean of round equal to mean of rectangle. Okay, and then the alternative is at least one is different. Okay, and then so the process there is you got to find your grand mean. So the grand mean would be 6.3 times, how many observations do we have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Am I counting this right? So we have 13 in each observation, right? So n is equal to 13, 13, and 13. Okay, so in that case, you know, all the 13s will cancel, but just for good measure, we'll do 13 plus 13 plus 13. So 6.3, 5.6 times 13 plus 6.0 times 13. Okay, and I did this earlier, and I got 5.967. Right, and then you'd have to fill out your ANOVA table with your source, your df, your sum of squares, your mean squares, and your f, and then you got between, within, et cetera, et cetera, et cetera. Okay, and you guys did this on the quiz this past week, and I think most of you got this these questions correct. So so that's what we would do. All right, I got like 1 minute left here. Let's just do another one here. Okay, let's look at 13 to 10. This is this problem goes across 2 pages here, so let me just oh, what did I do? Oh, here we go. We'll call it a day. A sample of 15 patients was randomly split into 2 groups as part of a double-blind experiment to compare 2 pain relievers. The 7 patients in the first group were given Demerol and reported the following numbers of hours of pain relief: 2, 6, 4, 13, 5, 8, 4. And the 8 patients in the second group were given an experimental drug and reported the following numbers of hours of pain relief: 0, 8, 1, 4, 2, 2, 1, 3. Okay, how might these data be analyzed? Okay, so we have, so our response is the hours of pain relief. Okay, pain relief, and we have 2 groups, right? We have Demerol versus experimental drug. Okay, and these are independent groups. What we do, so we might maybe use a t-test for independent groups, but the problem is we have small samples. Okay, so can we use central limit theorem? And the answer is maybe not. Okay, we have small samples, and so the question is, small samples are okay if there are no outliers. So do we have outliers? Okay, and so if we look at this data set, we actually do. So if I put this in order, got 0, 1, 1, 2, 2, 3, 4, and 8, right? So here's our median. Oh, wait. 1, 2, 3, 4, 5, 6, 7, 8. Okay. All right. So Q1 is equal to 1. Q3 is 3.5. IQR 3.5 minus 1. I have an IQR of 2.5. Okay. Upper fence and lower fence. Upper fence is Q3 plus 1.5 times the IQR. Lower fence is Q1 minus 1.5 times the IQR. I know this is like a callback, but let's check it out. Okay, so we'll do 3.5 plus 1.5 times the IQR of 2.5. What is that? I get 7.25. And then over here, I can do 1 minus 1.5 times the IQR, and I get negative 2.75. Right? So 8 is an outlier. Okay, and so that means we should use the Wilcoxon-Mann-Whitney. Okay. And then I won't go through the process here, but you would apply the Wilcoxon-Mann-Whitney test in this case. Okay. Sorry, we went a few minutes over here. I hope this was a little bit helpful as far as kind of just going over and seeing a whole bunch of the different topics from different sections. Okay, so we have a question. It says, do there have to be outliers in both groups or just one group to make us need to use non-parametric? Yeah, you only actually need outliers in one group. If you've got small samples and you've got outliers in either one of the groups, one or both of the groups, then it's an indicator that it might not be safe to use the central limit there. Okay. How do you know not to use the other non-parametric tests? So the other non-parametric tests that we covered are for paired data, okay? And this is not a situation where we have paired data, right? Paired data, it would be a paired data if we gave some patients Demerol, and then again, we gave them the same patients the experimental drug. But here we we have different patients, right? Actually, one group is 7 patients and the other group is 8 patients. So we have different patients. That's not a paired data situation. So the other non-parametric tests that we have, like the signed test and the signed rank test, are for paired data situations. And as far as the exam that on Thursday goes, I will make the scenarios unambiguous as far as which test should you use. So when you read it, there's only going to be one answer as far as the appropriate test to use in this scenario. Okay, that is all. It's been a pleasure to be your teacher this quarter, this summer session. I hope you've enjoyed the class. And so good luck as you study, and we will see you guys on Thursday for the final exam. I do see there was a question about quiz 5, and we'll do our best to get them graded, but I don't want to make any promises about for sure they will be graded before the exam or something. Okay. All right. Thank you, everybody. Have a good night. Good luck, and we will see you guys on Thursday.
Professor, is it okay if I ask where the